A-level, Pure 1, Series, the binomial expansion. We can think of the binomial expansion as the expansion of a bracket with two terms in it, raised to a power. So for example, if we expand 1 plus x all to the power n for different values of n, we get 1 plus x to the power 0 is just 1, because anything to the power 0 is 1. 1 plus x to the power 1 is just 1 plus 1x. 1 plus x all squared is equal to 1 plus 2x plus 1x squared. 1 plus x cubed is 1 plus 3x plus 3x squared plus 1x cubed. 1 plus x to the fourth is 1 plus 4x plus 6x squared plus 4x cubed plus 1x to the fourth. And to the power 5 we have 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the fourth plus 1x to the fifth. And 1x to the 6 is equal to 1 plus 6x plus 15x squared plus 20x cubed plus 15x to the 4 plus 6x to the 5 plus 1x to the 6. And if we just display the coefficients alone, we get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. What we notice is these numbers form a pattern. The numbers at the ends of each row are 1. Each other number in a row is the sum of the two numbers above it. So, for example, 1 plus 1 gives 2, 1 plus 2 gives 3, 4 plus 6 gives 10, 15 plus 6 gives 21, and so on. This triangle of numbers was discovered first in Europe by Blaise Pascal and is known as Pascal's triangle, although it was discovered elsewhere before that. We can also use Pascal's triangle to expand a plus b all to the n. Now we have a plus b to the 1 is equal to 1a to the 1 plus 1b to the 1. A plus b all squared is 1a squared plus 2ab plus 1b squared. A plus b cubed is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And a plus b to the fourth is equal to 1a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the fourth. These could also be written for completeness sake in the form a plus b squared is 1a squared b to the naught plus 2a to the 1 b to the 1 plus 1 a to the naught b squared. And a plus b cubed is 1a cubed b to the naught plus 3 a squared b1 plus 3 a1 b squared plus 1 a naught b3. If we expand a plus b to the n and look at the terms, we see that the powers of a start at n and decrease to naught, the powers of b start at naught and increase to n, and the coefficients are the numbers in the Pascal triangle row starting with 1n. So let's have a look at a few examples that show how we can expand a binomial expression. In 1, we want to expand x plus 5 to the power 4. Well, to solve this, we can start by putting in the powers of x and 5 and then adding in the coefficients later. So we start with x to the 4 5 to the 0 plus x to the 3 5 to the 1 plus x to the 2 5 to the 2 plus x to the 1 5 to the 3 plus x to the 0 5 to the 4. And then we add in Pascal's numbers. Now they have to start 1, 4. So that is 1, 4, 6, 4, 1. We can now simplify that. This is x to the fourth plus 4x cubed times 5 plus 6x squared times 25 plus 4x times 125 plus 625, which is equal to x to the fourth plus 20x cubed plus 150x squared plus 500x plus 625. In example 2, we want to expand 3a minus b cubed. Well, if we put some brackets in it, this is 3a plus minus b all cubed. So, if we first of all look at the terms and then put in the coefficients, we've got 3a to the 3, then 3a to the 2 minus b to the 1, then 3a to the 1 minus b to the 2, and then minus b to the 3. And we put in the coefficients, starting with 1 and 3, so that is 1, 3, 3, 1. Now that simplifies to 27a cubed minus 27a squared b plus 9ab squared minus b cubed. Well, so far we've seen one use of Pascal's triangle, and we can see it's quite important. If we draw the triangle so that the left-hand side is a vertical column, we can label the rows and columns. The first row is 0, which is just 1. Then row 1 has 1, 1. Row 2 is 1, 2, 1. Row 3 is 1, 3, 3, 1. Row 4 is 1, 4, 6, 4, 1. And row 5 is 1, 5, 10, 10, 5, 1. It's useful to have 0 at the top because then the row number is the same as the number in the second column. Now in the same way we have a column 0, a column 1, a column 2, a column 3, a column 4 and a column 5. Now there are two ways we can refer to Pascal numbers. The numbers in the table are either labelled in brackets n over r or NCR, where n is the row number and r is the column number. The bracket method tends to be used in pure maths and the C notation tends to be used in statistics. However, they are interchangeable. They both mean exactly the same thing. So, if we expand the bracket 1 plus x all to the power 4, we have 40x0 plus 41x1 plus 42x2 plus 43x3 plus 44x4. Or we could write that 4c0x0 plus 4c1x1 plus 4c2x2 plus 4c3x3 plus 4c4x4. If we expand 1 plus x all to the power n, then the term with x to the r is equal to nr x to the power r. Now there are at least 3 different ways of calculating nr or NCR. The first one is simply to draw out Pascal's triangle. Now this is useful if n is quite small and several values of r are needed. Example, expand a plus b to the power 5. Here 5CR is needed for all values of r from 0 to 5, and drawing the triangle will give them all quite quickly. We can look back to the previous page and see them. So a plus b to the 5 is 1 a to the 5 plus 5 a to the 4th b plus 10 a cubed b squared plus 10 a squared b cubed plus 5 ab to the 4th plus 1 b to the 5. An alternative method is to use a calculator. Now scientific calculators will have a button NCR. If we press 15 NCR 12 equals, this will give the value of 15C12, which in this case is 455. For example, on a Casio calculator, NCR is usually shift divide. So you would press 18 shift divide 6 equals to get 18,564, and that is the value of 18C6. Another way of doing it is introducing n factorial, which we write as n with an exclamation mark. Now, n factorial equals n times n minus 1 times n minus 2 and so on till we get to times 4 times 3 times 2 times 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5040. In fact, there will be a factorial button on any scientific calculator. Then we have the formula NR, or NCR, equals n factorial over r factorial times n minus r factorial. Let's look at an example. Evaluate 8/5. Now to solve this, 8/5 is equal to 8 factorial over 5 factorial times 3 factorial. And we can write that out in full. That is 8 times 7 times 6 and so on, down to 1, over 5 times 4 times 3 down to 1, times 3 times 2 times 1. Now we have 5 factorial on the bottom and effectively 5 factorial on the top, and so they can cancel. And that leaves 8 times 7 times 6 over 3 times 2 times 1, which is 8 times 7 times 6 over 6, which is 8 times 7, or 56. In part 2, we're asked to evaluate 12/8. Well, that's 12 factorial over 8 factorial times 12 minus 8 factorial, or 12 factorial over 8 factorial times 4 factorial. So we can write out 12 factorial in full, and underneath write 8 factorial in full, and 4 factorial in full. Now 8 times 7 and so on down to 1 cancels top and bottom. And then 12 on the top cancels with 4 times 3 on the bottom. And so we're left with 11 times 10 times 9 over 2 times 1, which is 990 over 2, or 495. Now we can actually check this if we use a calculator. We simply type in 12 NCR 8 equals, and the calculator will give us the answer 495. In example 2, part 1, we're asked to find the term in x to the power 6 in the expansion of 2 minus 3x to the power 9. Well, we want the term which includes minus 3x all to the power 6. That is 9/6 times 2 to the power 3 times minus 3x to the power 6. Now, if we write out the expansion of 9/6, that's 9 factorial over 6 factorial times 3 factorial times 8 times 729x to the power 6. We see 6 factorial cancels top and bottom, and that leaves us 9 times 8 times 7 over 3 times 2 times 1, which is 84, times 8 times 729x to the power 6. Well, that works out to be 489,888 x to the power 6. Now in part 2, we're asked to find the term in x to the power 4 in 2x plus 5 over x all to the power 10. Well, to get x to the power 4, we want the 2x raised to the power 7 and the 5 over x raised to the power 3. So that is 10/7 times 2x to the power 7 times 5 over x all to the power 3, which gives us 10 times 9 times 8 and so on down to 1 over 7 times 6 times 5 down to 1 times 3 times 2 times 1. Now we can cancel 7 factorial top and bottom, and that leaves us with 10 times 9 times 8 over 3 times 2 times 1. Then we've got times 2 to the 7 times x to the 7 times 5 cubed over x cubed, which gives us 120 times 128 times 125 x to the power 4, which is equal to 1,920,000 x to the power 4.